When we think about time, we often consider how things move from being organised to disorganised. This shift is explained by the second law of thermodynamics, which states that entropy or disorder in an isolated system tends to increase over time. Imagine you have a pack of cards that starts off perfectly ordered. As you shuffle, the order breaks down and the deck becomes more and more randomised. This increasing randomness is a reflection of growing entropy, which drives the arrow of time forward. However, the concept of dynamic symmetry suggests that this progression from order to disorder is not as straightforward as it might seem. Instead, it proposes that complex systems inherently balance stability and instability, allowing for the emergence of organised structures from apparent randomness, whilst also permitting seemingly stable states to exhibit chaotic behaviour under certain conditions. The concept of entropy was introduced in the 19th century by Rudolf Clausius. He noted that in any natural process, there's a tendency for energy to spread out, for systems to become more disordered. This tendency isn't just a neat mathematical rule, it underpins why time seems to move in one direction. Think about how an ice cube melts in a warm room. It transitions from a structured, low-entropy state, or solid ice, to a more disordered, high-entropy state, or liquid water. You never see the reverse happening spontaneously, because it would require a decrease in entropy, which is incredibly unlikely according to the second law of thermodynamics. However, dynamic symmetry reveals that this process is more nuanced than a simple progression from order to disorder. The melting ice cube, while becoming more disordered at a macroscopic level, may be creating new forms of order at the molecular level. The water molecules, freed from their rigid crystal structure, can now form new dynamic patterns of hydrogen bonds. This illustrates how order and disorder can coexist and transform across different scales within the same system. Our understanding of symmetry in the context of the arrow of time challenges the traditional notion of symmetry as a rigid objective property. Instead, it reveals symmetry as a fluid and subjective concept, adapting to the observer's perspective and the system's state. What appears as a progression from order to disorder from one vantage point may be perceived as the emergence of new forms of order from another. The symmetry between past and future, order or disorder, can shift and morph based on factors such as scale of observation, choice of variables, or even the observer's definition of order. This fluid concept of symmetry provides a more nuanced framework for understanding the arrow of time and its manifestations across different scales and systems. The idea that the universe started in a state of very low entropy is key to understanding the arrow of time. The Big Bang theory suggests that the early universe was incredibly hot, dense and ordered. As the universe expanded, entropy increased. This ongoing rise in entropy sets the stage for the forward march of time. The large-scale structure of the universe, from galaxies to the cosmic microwave background radiation, reflects this journey from order to disorder. However, dynamic symmetry suggests that this cosmic evolution is not a simple progression from order to disorder. As the universe expands and cools, new forms of order emerge. The formation of galaxies, stars and planets represents the creation of complex, organised structures from the initially uniform cosmic soup. This illustrates how the arrow of time, viewed through the lens of dynamic symmetry, involves not just the increase of entropy, but also the emergence of new forms of order at different scales. But why does entropy increase? Statistical mechanics, developed by Ludwig Boltzmann and James Clerk Maxwell, offers a microscopic view. They showed that for a vast number of particles, like gas molecules in a box, there are many more ways for these particles to be arranged in a disordered state than in an ordered one. Boltzmann's H-theorem mathematically demonstrated that entropy tends to increase because disordered states are statistically favoured. This provides a statistical foundation for the second law of thermodynamics, and it explains why we observe the arrow of time. Dynamic symmetry extends this understanding by suggesting that within this overall trend towards disorder, pockets of order can spontaneously emerge. This is evident in phenomena like self-organisation, where complex ordered structures arise from simple interactions between components. The formation of convection cells in heated fluid, or the emergence of patterns in chemical reactions, are examples of how order can arise within systems that are generally moving towards greater entropy. Now, this brings us to a paradox. The fundamental laws of physics are time symmetric. They don't care if time runs forwards or backwards, and yet we observe a clear direction in time. Boltzmann argued that while individual particle interactions are reversible, the overall tendency for systems to increase in entropy creates the macroscopic arrow of time we experience. Dynamic symmetry offers a resolution to this paradox by suggesting that the arrow of time emerges from the interplay between microscopic reversibility and macroscopic irreversibility. At the quantum level, processes may be time symmetric, but as we scale up to larger systems, the statistical tendency towards higher entropy states creates the appearance of a preferred direction in time. Cosmology, the study of the universe, also plays a significant role in this narrative. The Big Bang theory describes a universe that started in a low entropy state and has been increasing in entropy ever since. Gravity adds another layer to the story. In the early universe, matter was fairly evenly spread out. Over time, gravity caused matter to clump together, forming stars, galaxies, and other structures. This clumping seems like an increase in order locally, but actually contributes to the overall entropy of the universe by releasing energy and spreading it out. Dynamic symmetry provides a framework for understanding how these seemingly contradictory processes, the overall increase in entropy and the local emergence of order, can coexist. It suggests that the arrow of time in cosmology is not just about the universe becoming more disordered, but about the continuous transformation and redistribution of order and disorder across different scales. Information theory, pioneered by Claude Shannon, offers yet another perspective. In this field, entropy measures the amount of uncertainty or information content in a system. A highly ordered system has low information entropy, meaning it can be described with fewer bits of information. Conversely, a disordered system has high information entropy. As systems evolve and entropy increases, the amount of information required to describe them grows, reflecting increasing complexity and disorder. Dynamic symmetry extends this concept by suggesting that information, like physical systems, can exhibit both order and disorder simultaneously. For example, in complex systems like the human brain, highly structured neural networks coexist with seemingly random firing patterns. This balance between structure and randomness may be crucial for information processing and the emergence of complex behaviors. The irreversibility of information processing aligns with the second law of thermodynamics and reinforces the arrow of time. When information is transformed or transferred, some of it is inevitably lost or degraded, contributing to an increase in entropy. This loss of information is another manifestation of the temporal asymmetry we observe in nature. However, dynamic symmetry suggests that this information loss can also be viewed as a transformation. What appears as a loss of information at one level may be the creation of new information or patterns at another. This perspective aligns with recent developments in quantum information theory, where information is not necessarily lost, but can be scrambled or distributed in ways that make it practically irretrievable. The symmetry between order and disorder is not just a theoretical concept, it's observable in the real world. One of the most captivating examples is the emergence of order from disorder. In thermodynamics, this phenomenon is described by dissipative structures, systems far from equilibrium that develop ordered patterns as they dissipate energy. Think about the formation of snowflakes, the branching patterns of rivers, or even the self-organization of biological organisms. These examples show how simple, repetitive processes can generate complex, ordered structures from seemingly random origins. Dynamic symmetry provides a framework for understanding these phenomena by suggesting that order and disorder are not opposites, but complementary aspects of complex systems. The formation of a snowflake, for example, involves both the random motion of water molecules and the highly ordered process of crystal formation. The resulting structure embodies both order in its symmetrical shape and disorder in its unique, unrepeatable pattern. Fractals, which are geometric shapes that exhibit self-similarity at different scales, beautifully illustrate the symmetry between order and disorder. Fractals are found throughout nature, from the intricate structures of snowflakes to the branching patterns of trees and rivers. They demonstrate how complex ordered patterns can emerge from simple, disordered processes. Dynamic symmetry suggests that fractals aren't just mathematical curiosities, but fundamental expressions of how nature balances order and disorder across different scales. Life itself is a testament to the emergence of order from disorder. Living organisms maintain and create order locally by consuming energy and increasing the entropy of their surroundings. This process is governed by the principles of thermodynamics and statistical mechanics. Living systems are quintessential dissipative structures. They extract energy from their environment, convert it into work, and release waste heat, thereby increasing the entropy of their surroundings. This continuous flow of energy allows organisms to maintain their highly ordered states and carry out the processes necessary for life. Dynamic symmetry provides a new perspective on this process by suggesting that life is not just about maintaining order in the face of increasing entropy, but about continuously transforming and redistributing order and disorder. The complex biochemical processes within cells, for example, involve both highly ordered enzymatic reactions and the seemingly random Brownian motion of molecules. This balance between order and disorder may be crucial for the adaptability and resilience of living systems. The process of evolution further illustrates the interplay between order and disorder. Genetic mutations introduce randomness and variability, while natural selection favours advantageous traits, leading to the emergence of increasingly complex and ordered organisms over time. This balance between random variation and selective pressure drives the evolution of life, reflecting the symmetry between order and disorder. Dynamic symmetry suggests that evolution is not a linear progression towards greater complexity, but a continuous exploration of the balance between order and disorder. This perspective aligns with recent developments in evolutionary theory, such as the concept of punctuated equilibrium, which proposes that evolutionary change occurs in rapid bursts interspersed with periods of relative stability. These concepts have profound implications for our understanding of time. They suggest that time's arrow is not an intrinsic property of the universe, but an emergent phenomenon arising from the interplay between order and disorder. This perspective has the potential to unify various branches of physics under a common framework. Dynamic symmetry proposes that the arrow of time emerges from the continuous transformation and redistribution of order and disorder across different scales and systems. This view challenges the notion of time as a simple linear progression and suggests that our perception of time's direction may be intimately tied to how we define and measure order and disorder. At the most fundamental level, the laws of physics, such as those governing quantum mechanics and general relativity, are time symmetric. This means they do not distinguish between past and future. However, the macroscopic world we observe is time asymmetric due to the increase in entropy. This disparity highlights the significance of initial conditions and the role of statistical mechanics in translating time-symmetric laws into the time-asymmetric reality that we experience. Dynamic symmetry offers a potential resolution to this paradox by suggesting that the arrow of time emerges from the interplay between microscopic reversibility and macroscopic irreversibility. It proposes that time's direction is not absolute, but context-dependent, emerging from how systems balance order and disorder across different scales. Quantum mechanics introduces another layer of complexity to the discussion of time's arrow. The wave function of a quantum system evolves according to the Schrödinger equation, which is time-symmetric. However, the process of wave function collapse during measurement introduces an element of irreversibility, contributing to the macroscopic arrow of time. Dynamic symmetry suggests that this quantum measurement problem may be related to how information is transformed and redistributed across different scales. The apparent collapse of the wave function could be viewed as a rapid redistribution of order and disorder, rather than a fundamental irreversible process. This perspective aligns with recent developments in quantum information theory and may offer new approaches to understanding the quantum classical transition. The arrow of time also has profound cosmological implications. The low entropy state of the early universe and the ongoing increase in entropy provide a framework for understanding the evolution of cosmic structures. As the universe continues to expand and evolve, the interplay between gravitational forces and thermodynamic principles will shape its ultimate fate, whether through continued expansion, heat death, or a potential cyclical model. Dynamic symmetry offers new perspectives on these cosmological questions. It suggests that the evolution of the universe may involve not just an increase overall in entropy, but a continuous transformation and redistribution of order and disorder across different scales. This could have implications for our understanding of dark energy, dark matter, and the long-term fate of the universe. Non-equilibrium thermodynamics explores the behavior of systems far from equilibrium, where traditional thermodynamic principles may not fully apply. Investigating how these systems generate and maintain order can shed light on the mechanisms driving the arrow of time and the emergence of complexity in the universe. Dynamic symmetry suggests that these non-equilibrium states may be key to understanding how order and disorder are continuously transformed and redistributed in complex systems. The study of complex systems and self-organization offers a rich avenue for exploring the symmetry between order and disorder. By examining how simple rules and interactions give rise to complex behavior, researchers can gain a deeper understanding of the processes that underpin temporal asymmetry and the emergence of order from disorder. Dynamic symmetry provides a conceptual framework for this research, suggesting that the key to understanding complex systems lies in how they balance and transform order and disorder across different scales. It's evident that the concept of dynamic symmetry provides a powerful framework for understanding the arrow of time. By examining the principles of thermodynamics, statistical mechanics, cosmology, and information theory through this lens, we can see how the interplay between randomness and structure shapes the directionality of time in a more nuanced and complex way than previously thought. The increase in entropy, driven by the fundamental laws of physics, underpins the irreversible flow of time from past to future. But this process is not a simple progression from order to disorder. Instead, it involves a continuous transformation and redistribution of order and disorder across different scales and systems. The emergence of order from disorder, evident in both natural and biological systems, illustrates the profound connections between the microscopic and macroscopic worlds. Dynamic symmetry reveals that these processes are not contradictions of the second law of thermodynamics, but integral parts of how complex systems evolve and maintain themselves over time. As we continue to explore these relationships, we deepen our understanding of the fundamental nature of time and the intricate dance between order and disorder that defines our universe. The concept of dynamic symmetry challenges us to rethink our notions of time, symmetry, and the nature of reality itself. It suggests that the universe is not simply running down towards a state of maximum disorder, but it's continuously creating new forms of order and complexity as it evolves. This perspective has profound implications, not just for physics and cosmology, but for our understanding of life, consciousness, and even the nature of knowledge itself. It encourages us to see the world not as a collection of isolated deterministic systems, but as a vast interconnected web, a network of dynamic processes constantly balancing and transforming order and disorder across all scales of existence.